Example 3. A curve has equation y is equal to 5 over 2 minus 3x and passes through the point P minus 1, 1. Find the equation of the tangent to the curve at P and find the angle that this tangent makes with the x-axis. The solution. We know that y is equal to 5 times 2 minus 3x raised to the power minus 1 from the laws of indices. This would then imply that if we are going to find the derivative of y, we can use the substitution method that we covered in part 3. Make sure to check out the differentiation play series part 3. So we let u be equal to f of x, and the f of x is 2 minus 3x, the inner function, and our du dx becomes minus 3. The second step. This implies that our y becomes 5 times u to the power minus 1, and our dy du becomes minus 5 u to the power minus 3. And lastly, our dy dx is going to be obtained by substituting for the dy du times the du dx which we obtained in steps 2 and 3. Doing so, we are going to find minus 5 u to the power minus 2 times minus 3. We move on to substitute for the u which we obtained in step 1 so that we get 15 times 2 minus 3x to the power minus 2. Therefore, the gradient of the tangent at P is given by m, so we substitute where we have x in our dy dx, we substitute that with the minus 1, which was the x-coordinate of the point P. In so doing, we can simplify further so that we have m is equal to 15 times 5 to the power minus 2. Then our m becomes 15 times 25 to the power minus 1, and simplifying further, we get m is equal to 3 over 5. Welcome to Numbers Simplified. In this channel, we seek to simplify and solve numerical problems. Today, we'll be looking at the differentiation and covering tangents and normals. This is part 4. And I encourage you to check out the following videos. The differentiation playlist, part 1 to part 3, where we covered differentiation from first principles, substitution, as well as the introduction to differentiation, so that you catch up on what we have covered so far. I also encourage you to check out other playlists, like the integration, polynomial, quadratics, among others. Moving on with differentiation. Recall, dy dx is known as the gradient function for a curve y is equal to f of x. At the point px1, y1, the gradient of the curve is given by m is equal to f prime of x1. This is the same gradient to the tangent at the point px1, y1 of a curve. So supposedly we have this graph right here. We can see the tangent is the line that touches the curve only at one point, and the line that is perpendicular to that tangent is known as the normal. Then of course, the equation of the tangent that is through the point px1, y1 is derived from. We know that y minus y1 over x minus x1 is equal to m, which is the gradient of a line. So we can actually go on to clear the fraction by multiplying by x minus x1, so that we get y minus y1 is equal to m times x minus x1. Then solving for y, we are going to have this bit. Then our final step would have y is equal to mx plus y1 minus mx1. So we can substitute for this x1, y1, and we know that our m comes from the dy dx. Now, we also recall that a normal is a line perpendicular to a tangent. If the gradient of a tangent is given to be m, then the gradient of the normal is given to be minus 1 over m. This means that the equation of the normal through the point px1, y1 is given by, we simply substitute for m, since our gradient this time around is 1 over m, and that is a negative value. So we solve for y so that we get this bit. So that is how we would get the equation of the normal through the point px1, y1 at a curve. Now that we have covered the theory of finding the equation of the tangent and the normal, it's worth noting that if m, the gradient, is equal to 0, the equation then of the tangent becomes y is equals to y1, simply because the x1 and the x will all go to 0. And this would imply that the equation of the normal that is perpendicular to that particular tangent becomes x is equals to x1, the vertical line. Let's look at example 1. A curve passes through the point A, which has coordinates 2.5, and has the equation y is equals to 8 over x plus 2 squared. Find the equation of the tangent to the curve at the point A. B. Find the equation of the normal to the curve at the point A. The solution. We know that we can express y in terms of 8 times x plus 2 raised to the power minus 2, and we take that from the laws of indices. Make sure to check out our indices video. Now, we have this type of a problem, so we can find the derivative dy dx by using the substitution method, and we covered this one in our part 3. So I encourage you to check it out. This is differentiation playlist and part 3, using substitution and the chain rule. So we let u be equal to f of x, the inner function within the parentheses or brackets. So u is equal to x plus 2, and implying that the du dx is equal to 1. The second step, this would imply that our y is now equal to 8 times u to the power minus 2 because we have substituted for the x plus 2 by u. From there, we go on to find dy du. And of course, using the rules of differentiating powers, we are going to get our dy du becoming minus 16 u to the power minus 3. The final step. In order for us to find the dy dx, we would then substitute the dy du and the du dx. We know our dy du from step number 2, which was minus 16u to the power minus 3, and our du dx was equal to 1. We multiply. In so doing, we also move on to substitute back for the u with the x plus 2 from step number 1, implying that our dy dx is equal to minus 16 times x plus 2 to the power minus 3. Great then. Now that we have our gradient function, this means that we can find our gradient at the point A. We know the x-coordinate of the point A, which was a 2. All we have to do is substitute for the x by the 2 that we have, implying that our m is equal to f prime of 2. Now from the dy dx, we substitute for x by a 2, so that we have a minus 16 times 2 plus 2 raised to the power minus 3. This simplifies to minus 16 times 1 over 64, which is equal to minus 1 over 4. So that will be the gradient of the tangent. Now, to find the equation of the tangent, looking at the formulae that we have on our left-hand side, the first one in the box, we can substitute for the y1, which is a half. Then we also substitute for the x1, which is a 2. In so doing, we come up with this equation. Simplifying it further, we are going to get y is equals to minus 1 over 4x plus y, or clearing all the fractions by multiplying by the denominator, which is a 4. That would give us a 4y is equals to minus x plus 4. Take note, all the terms were multiplied by 4 so that we clear the fractions. Part A is answered. Now we move on to answer part B, but we're going to make use of the information that we obtained from part A. We obtained the gradient of the tangent m to be equal to minus 1 over 4. This would imply that the gradient of the normal at A is equal to 4 from the relationship that we have, and the gradient of the normal at A is going to be m is equal to 4, fair and fine. Now, what we go on to do is to substitute for the m using the second equation we have on the left, that is the one in the rectangle, the second rectangle. So in so doing, we are going to have this equation. And of course, we know that simplifying this equation, we are going to have y is equals to 4x plus half plus minus 4 times 2. And simplifying this further, we get y is equal to 4x minus 15 over 2. Or in simple terms, if we clear the fractions by multiplying all terms by 2, we are going to get 2y is equals to 8x minus 15. And this is how we solve the part B of example 1. Moving on to example 2. The normal to the curve y is equal to 4 minus square root of x at the point P 16 minus 4 meets the axis at the point Q. A. Find the equation of the normal PQ, and B. Find the coordinates of Q. The solution. We know that we can express y in terms of 4 minus 2x to the power half. This would then imply that the dy du is going to be minus 2 times half times x raised to the power minus half. And simplifying that further, we are going to get a minus x raised to the power minus a half. The gradient of the tangent at point P, where we have x in the divided x, we substitute with the x coordinate of the P, which is a 16. So this would mean that m is equal to minus 16 raised to the power minus a half. And simplifying this one further, we are going to get a minus 1 over 4 as the gradient of the tangent at P. Then the gradient of the normal at P would simply be 4. So the m would be 4. Then the equation of the normal is going to be given by y is equal to 4x minus 4 times 16, because we are using the same m, which was the gradient of the tangent, but of course the gradient of the normal is 4, so implying that if we substitute for the gradient of the normal, which is a 4, and substitute for the x1, which is a 16, we can actually simplify this in order to get y is equal to 4x minus 68. Moving on to part B. For coordinates of Q, we are going to use the equation of the normal. We set the y to be equal to 0, as this is the point where the P or the normal meets with the x-axis. So at the x-axis, we know that y is equal to 0, and that is the point Q. So with that, we move on to solve for x by moving the 68 to the other side so that it becomes positive since it was negative. Then we divide throughout by 4 so that we obtain our x of 17. Now that x is equal to 17, we know that the y coordinate is equal to 0. Therefore, the coordinates of point Q are 17, 0. And that's how we solve part B of example 2. Now, let's move on to example 3. A curve has equation y is equal to 5 over 2 minus 3x and passes through the point P minus 1, 1. Find the equation of the tangent to the curve P and find the angle that this tangent makes with the x-axis. The solution. Y is equal to 5 times 2 minus 3x raised to the power minus 1. Of course, we would recall that we can use the substitution method, or known as the chain rule. In so doing, we let the u be equal to the f of x, the inner function, as our first step, so that we obtain the du dx to be minus 3 when we differentiate the f of x. The second step is to find the dy du, since we know that when we substitute for the 2 minus 3x with the u, we are going to get a y which is equal to 5 times u to the power minus 1, implying that our dy du is equal to minus 5 u to the power minus 2. Then the last step is to find dy dx, which is dy du times du dx, which is equal to minus 5 times u to the power minus 2 times minus 3, substituting for the dy du which we obtained from step number 2 and the du dx that we obtained from step number 1. This means that our dy dx is equal to 15, 2 minus 3x to the power minus 2. Great. Now that we have our dy dx, we can go on to find the gradient of the tangent at the point P. Since we have the x-coordinate at point P, which is a minus 1, so in our dy dx, we are going to substitute for that x with the minus 1, implying that the gradient m is equal to 15 times 2 minus 3 times minus 1 raised to the power minus 2. Simplifying further, we are going to have m being equal to 15 times 5 raised to the power minus 2, which is the same as 15 divided by 25, giving us m of 3 over 5. Then the equation of the tangent at point P is going to be, we know the gradient of that particular tangent, and we also have the y1 and the x1. So making use of the formula that we have on the left-hand side, and to be precise, the first one, we are going to substitute. Since we know what our x1 is and our y1 is, we get to that, implying that the equation of the tangent at P is equal to y is equal to 3 over 5 x plus 8 over 5. And of course, we can actually clear the fractions by multiplying by the denominator, which is a 5, throughout, so that we get 5y is equal to 3x plus 8. Great, then we have dealt with the equation of the tangent that passes through the point P. Now, we are asked to find the angle that this tangent makes with the x-axis. So we know that a tangent is equal to tan theta, which is equal to 3 over 5. So if tan theta is equal to 3 over 5, what it means is that we are going to introduce the arctan on both sides of the equation so that the arctan and the tan cancel out. We have theta on the left-hand side. Then we introduce the arctan on the right-hand side as well, so that we have arctan of 3 over 5. And this would then simplify to 31 degrees. That's how we solve question 3. Now, let's dive into the last example. Example 4. The normal to the curve is equal to y is equal to 2x squared plus kx minus 3 at the point 3 minus 6 is parallel to the line x plus 5y is equal to 10. A, find the value of k, and B, find the coordinates where the normal and the curve meet again. The solution. So for part A, from the line that we're given, x plus 5y is equal to 10, if we rearrange by making y the subject of the formula, we get y is equal to minus 1 over 5x plus 2. Let's label this equation 1 for ease of reference, and it's easy to see from this equation that the gradient of this particular line is minus 1 over 5. So if that is the case, then that would mean that our m is equals to minus 1 over 5. Then the gradient to the tangent is equals to 5. Since what we had was the gradient of the normal of minus 1 over 5, then the gradient to the tangent is a positive 5. Now, considering the curve y is equals to 2x squared plus kx minus 3, we label this one equation 2 for ease of reference once again. Finding the derivative of this particular curve, we are going to get dy dx of 4x plus k. Now, we know that at this particular dy dx, we are going to get the gradient of the tangent. So at the specific point, which is point with coordinate, x coordinate 3, f prime of 3 being 4 times 3 plus k is equals to 5. Now solving for k, we are going to get 12 plus k is equal to 5. This would imply that k is equal to minus 7. Now that we obtained the value of k, we have answered part A. We move on to part B. For part B, the equation of the normal at the point 3 minus 6 was given from equation 1, and now that we have that particular gradient to the particular normal, we can now move on to substitute for the y1 and the x1 so that we get the equation to the normal passing through the point 3 minus 6. So we substitute for the x1 and the y1. The x1 was a 3 and the y1 was a minus 6. So making use of the formula that we have, the second formula there, we are going to find that we have y is equal to minus 1 over 5x minus 27 over 5, and labeling this equation 3. So now we have 3 equations. Now we want to find where these lines intersect. So one is a straight line and the other one is a curve. So we are going to equate equation 2 and equation 3 because this is where they would intersect. In so doing, we are going to have 2x squared minus 7x minus 3, which we obtained from equation 2 after substituting for the value of k we obtained of a minus 7, is equals to equation 3 minus 1 over 5x minus 27 over 5. Now, the first thing that we can do is clear the fractions by multiplying throughout by the denominator of 5 throughout. So each and every term will be multiplied by a 5. In so doing, we also group the like terms, shifting the x terms to be on the left-hand side, as well as the non-x terms. We are going to get 10x squared minus 34x plus 12 is equals to 0. We see that we also have a common factor, which is a 2, so we can divide throughout by a 2, so that we have 5x squared minus 17x plus 6 is equals to 0. With that, we are going to solve for x, and I choose to use the factorization method because that's one method I enjoy working on. And I encourage you to check this video out on our quadratics list, where we use the factorization method in solving our problems. So with that, what I have is 5x minus 2 times x minus 3 is equals to 0. Now equate each term to 0 so that I have 5x minus 2 is equals to 0 or x minus 3 is equals to 0. Solving for x, I get x is equals to 2 over 5 or x is equals to 3. Now I know that one of the point was a given point. The x is equals to 3 is a point, or rather a coordinate of a point that was given. So I wouldn't worry myself about it because I know that it's going to give me a y coordinate of minus 6 since it was given already. Now I focus on the first term. X is equals to 2 over 3. Now, when you check out the left-hand side from the graph, this is just a sketch of what we have now. We have a curve, y is equals to 2x squared minus 7x minus 3, and the line y is equals to minus 1 over 5x minus 27 over 5. These two intersect at 2 points. One of the point is 3 as I have it there. Then I'm looking for the other point, which is before 3 and probably after 0, or the origin. Now, proceeding. In order for me to find the y coordinate, what I would have to do is substitute for the x value in either equation 2 or equation 3. So I choose to use the linear equation. This is equation 3 because it's simpler. So substituting for x by 2 over 5, I'm going to have that so that at the end of the day, my y is minus 137 over 25. Therefore, the coordinates are 2 over 5 and minus 137 over 25. If you have made it thus far, I say congratulations to you. I'll leave you with the following task. The curve y is equals to 12 over 2x minus 3 minus 4 intersects the x-axis at P. The tangent to the curve at P intersects the y-axis at Q. Find the distance PQ. Thank you so much for watching Numbers Simplified. Make sure you like, share, and subscribe so that you don't miss out on any of our future uploads. Thank you so much once again.